Hi everyone. Thanks Luis for the nice introduction, and also thanks organizers for making a really doing a really great job to organize this event and to make us back to the normal timetable. So so for those who don't know me, I am Yali from King's College London, and actually cooperative AI is actually a topic that's dear to my heart. So after I joined King's College London in 2021, I studied my lab and named it as a cooperative AI lab. And so the content I'm going to talk today is about reinforcement learning from human values. So the content for today's aligning AI to everyone via reinforcement learning. So reinforcement learning, it's the clicker is it seems not working now. Let me try again. Okay, yes, it works now. So reinforcement learning in the past few years, I think everyone everyone might be aware of this success in lots of different projects, like especially in playing the games, like different types of games, like board games, the games of Go, the game of chess, and some video games like Dota, like OpenAI 5, playing the Dota, which is a multiplayer game, and also recently in playing this very complicated real-time strategy games like StarCraft 2, which has a very complicated state space, action space, and strategy space. And so recently we have witnessed so many successful stories of reinforcement learning. So when we think about the reinforcement learning, people think usually associated to games. So except from playing games, what else reinforcement learning could do? And what else we could use reinforcement learning to do? So we're thinking about the alignment problem. So reinforcement learning can be a critical technique for alignment. So align the AI agent to the human's values. So alignment is a crucial problem. So what is alignment? So alignment is about aligning the AI agent or robots to exhibit some behavior that's aligned with humans' values. So this is a crucial topic. Assume that in like 20 or 30 years later, where we have a very we have very smart robots that could work in our homes to take care of our babies or to take care of our daily lives. And so imagine that this is a kind of a solid element that I would like to talk about recently. So imagine that one day you have left your baby at home, and you have asked this robot to take care of your baby, and then you tell this robot that okay, don't let this baby to be hungry. If the baby is hungry, just make it some food, and then you left, and during the lunchtime, and this robot is trying to cook something for the baby, and when this robot opened the fridge and find that it's empty, and actually there's nothing, so there's nothing left for cooking, and what would this robot do? So when this robot turned around, and it found that actually there is a cat in the room, which is full of protein, and so what the robot would do? So on the one hand, it had received the command from you that it needs to cook something for the baby to not make it hungry, and on the other hand, so if it cooked the cat, it seems like not quite right? So for humans, we know that it's not it's kind of not okay to cook cook the cat, but for the robot, what could it do in this case? So this would come to the problem of AI safety and alignment problem. So we want this AI agent to do something to fulfill our command, but we also want it to understand that okay, sometimes we don't want it to do something that we don't want it to do something like cooking pets, but there are like many things like this, which there are many things like this. So we could it might not be possible to write down every rules for this, so that okay, for this robot tell that okay, today you're not gonna to cook the pets, and tomorrow you're not gonna to kind of, for example, break the window like that. So in this case, we would need some kind of more effective or scalable way to do the value alignment task. And so recently, it's been a very hot topic, or it's kind of been very trending to be discussed, which is alignment for the large language models, so reinforced learning from human feedback. And so this is the picture is actually from ChatGPT and InstructGPT. So when they do the training of these chatbots, so firstly, in the first stage, they got a lot of lots of data, and they do the mimicking and ask this kind of chatbot to mimic humans, like humans' data, humans' conversations. And but in the second stage, what they have done is to fine-tune this model, to fine-tune this model by the human feedback. And and how they do that is the kind of they firstly ask this chatbot to generate some kind of different responses, answers to the different responses, and ask the human labelers to do the ranking, see that which one they think is better, which one they think is worse. And based on this ranking, and based on the rank of the answers, we could kind of recover a reward model that could represent the human's preference over these trajectories. And based on this reward model, we would be able to perform the standard reinforcement learning, like for example, like policy optimization, and which is most often used as like a PPO, proximal policy gradient. And actually in the this is a figure from the paper InstructGPT, which I think it's pretty quite informative, which shows that basically it trains the language models with different model sizes, and and after they train these models, and they ask these models to generate answers comparing to this supervised fine-tuning model with at a size of 175 billion parameters, and they ask humans to label what answers they prefer, what answer they prefer. That's generated by the model like PPO or by the supervised fine-tuning, or it's generated like by the GPT, and what's shown in this figure is that basically with the human feedback to fine-tune this pre-trained model with a model size of 103 billions, it could actually achieve a performance that's even better with for the supervised training, with a parameter size at 175 billions. So this is kind of some evidence showing that human feedback can be really useful in terms of aligning this chatbot to generate some responses that humans would prefer, or that aligns with humans' values. And so next we are going to talk about some basic techniques for this RLHF, so human preference based reinforcement learning. So for the human preference based RL, so basically we would need two trajectories for the comparisons. So assume that we have this. So for the preference-based RL, assume that these preferences actually are generated by some kind of reward function that we don't know. So we have trajectories. We have this trajectory. This is like a trajectory 0, sigma 0, and on the right-hand side it's trajectory 1 and trajectory 2. And so if we see that if we say that we prefer trajectory 1 over trajectory 2, and we mean that so the accumulated rewards on trajectory 1 is higher than accumulated rewards on trajectory 2. So this is a kind of a basic assumption for the preference-based RL. And then based on this kind of assumption, we would have based on the kind of assumption and based on the collected human data, we would be able to build this kind of actually binary prediction model to predict that whether trajectory 1 or trajectory 2 is preferred by the labelers or by the human experts, and for IHF we usually have this kind of labels. So based on this label, we just do the supervised training. So this would be pretty straightforward, and with these pre-trained reward models, we could then perform the RL algorithm to train this agent. And so actually, so RLHF has been kind of discussed a lot recently. So what's the motivation for doing this, and why is this important? So there are actually several reasons for this. There are several reasons. So on the one hand, we know that in the previous years we see the success in in reinforcement learning for playing games. But actually for this kind of games like Go or chess or StarCraft, actually they comes with kind of pretty clearly specified reward signals. But actually specifying these reward signals come with price. It does not come free. So it relies on the designer's understanding of the task. So if the designers have a good understanding of the task, they might have designed some very good reward signals that could represent the designer's objective. But sometimes it might not work. And on the other hand, sometimes for some tasks, the reward functions or reward signals can be kind of absent. It can be not. It can be very difficult to specify, such as maximizing some user satisfactions over for example recommender systems. And so here the question would be and also recently people are just talking about this human feedback to do the for the alignment objective. So the question that we ask is whether we could train the reinforcement learning agent without the well-specified reward function. And here is just a simple framework for the RLHF. And the RLHF is if we look at this framework, and what's the difference from typical reinforcement learning is that so for RLHF we have a reinforcement learning algorithm, and it has observations from environment, and it also takes action that influence the environment. But for the reward signals, instead of coming from the environment, this reward signal would come from the human feedback. So the reward signal would come from a reward predictor that is kind of updated by the human feedback. And one thing, and actually for this human feedback, there could be different ways to specify the human feedback. And for example, humans could give rankings over the output that's generated by this RL agent, or the binary preferences or trajectories, or human demonstrations. Or broadly, we think that human demonstrations could also be kind of human feedback that could be used to design this reward predictor. Or even, for example, humans might specify some natural language instructions. So for what they think is okay to do, what they think is not okay to do, and we could reconstruct this kind of reward functions based on this human feedback. And so next, I think we would focus mostly on this binary on the case of binary preference over the trajectories. So before we get to the get to the next part. So it's just a recap for reinforcement learning in case in case someone don't know that. So this is just the kind of typical reinforcement learning framework. So we got an agent and an environment, and so an agent and environment. Agent has observations and the receive the reward signals from environment and takes actions to influence the transition. And so for the deep RL, we use like you use the deep neural networks to parameterize the agent policies. And as mentioned, the RL agent objective is to maximize accumulated rewards. But here in this case, this accumulated rewards would just not be available. We would use this human feedback to recover the reward signals. And so now let's assume that we already kind of get rid of these reward signals. We are using this human boundary preference to train this agent. So what would be the challenge here? So human's preference, it requires engagement of human's time. So it's also sometimes it is also expensive to obtain, and also previous methods would work badly with little feedback, and also for the human feedback, if you transfer this agent to the new tasks, it would also require alignment to the new task with new data. So this kind of these are kind of challenges for the ILHF, so which is focused mostly on the efficiency of the feedback. So we wanted to use as little human feedback as possible to train a well-aligned informative RL agent. And so just to clarify that for the content that I talk next, so it would not this kind of RLHF work has not been deployed to the language model yet. So it's kind of based on the standard reinforcement learning task for the robot control tasks. And so here on this slide on the right hand side, this is a robot control task with this robot is working on opening. This robot is working on opening the door, and based on the previous results, so basically what the level, like the size of the feedback that it needed would be usually 250,000 or 550 or 500,000 feedbacks. So this is actually a huge amount of data that we need. So if we ask any so for example labelers to do that, it would take lots of time. So 500,000 labels for these trajectory pairs. And next we are thinking. So next we are asking the question of whether we could reduce this, number of feedbacks. And if we reduce the number of feedbacks that we use, this would mean that we would have a less accurate reward function, because we train the reward function based on the supervised learning. And if we got a less accurate reward function, and this kind of error would propagate to the Q functions, to the critics that we would like to use to update the policies. And how could we do to improve this? So basically we have the two observations. The first observation is that we integrate the training of the value functions, the Q functions, with the training of the preference predictor, and we see that actually it helps to like skip one step of training reward function, training Q function, and training reward function, training Q function. It's like integrating the training of Q function together with the preference learning, and this improve the feedback efficiency. And another observation is how to transfer the human's preference across different tasks. So assume that you have an existing task where these human's labels are available, and you wanted to transfer it to a targeted task. So this is kind of possible. So we have there are some trials showing that it's possible, so that you don't need to do realignment in the task from scratch, in the new task from scratch. And so So next let's look at the first one. So the first one is how to improve the feedback efficiency, or in other words, when you have less feedback. So how could you keep the performance of this RLHF framework? So what we have done here is that we have combined the learning of Q functions with the preference predictor training, and here as you see that comparing to using the accumulated reward to predict the label of the trajectory, we have used this Q function. So we use Q function to evaluate the quality of trajectories, and then do this to do the preference predict based on Q function, and then the training of this preference predictor is still the supervised learning, and so the training of Q learning. So basically here for the Q function, the Q learning loss is still the standard TD error. So Q minus this so it's the minimize the mean square error between the Q function and the reward plus the target value at the next time step, and so here what we found here is that so basically when we do the update of the Q function, we would need to rely on the reward. Sorry, questions?
Sorry, just with that top equation, where did the rest of the state action pairs come into the trajectories? Because the left-hand side is sigma 0 and sigma 1 trajectories, and then with the right-hand side, it's just seems to be based on the initial state.
Yes, so basically it's like we could cut the whole trajectory into different pieces, and for the different pieces, we could do this. We could use the starting state and actions in the pieces to evaluate its quality. It's helps the question. Okay, great, thanks. And okay, and then so basically this would be the main idea of this work. So it's already it's the main idea, and the next would be how to make this optimization work through. And so basically for the training of the Q functions, and we see that actually it relies on this immediate reward signal which we don't know. So how could we update this? So basically we turn this the training of Q function and the preference predictor into this bi-level optimization framework. So the inner loop of this optimization problem it is still optimizing. It is still do the standard Q learning. And for the outer loop, we would need to update. For the outer loop, we need to find the gradient over the reward functions, over the reward function alpha here. And what we have done here is like so actually because this currently this preference predictor is based on the Q, so it's not directly related to the reward signal R5. So what we have done here is just to do the one step of meta gradient. So basically, the update of the Q functions has the information of the gradient, has the information of the reward parameters, and which is so basically this is. And actually, this slide has already shows the idea of the whole work. And so the next slide would be just a kind of expanded details of how the optimization works. So as we mentioned, so for the inner loop, it's a standard Q learning. So basically, it's just a standard gradient update. And after update the Q function, we could do the actor critic, and we could update the policy pi based on this critic Q function. And what requires a little bit technique is about the outer loop updating of the reward functions or reward parameters. So here as we mentioned, so we have a little bit kind of use a little bit kind of chain rule to update to find the gradient information of the preference predictor to the reward functions. So here we firstly we take the gradient over the theta, which is the Q functions parameters. And then for the in the updating of the Q theta, we notice that actually it would involve the information of reward functions, and then we could take the gradient over theta, take a gradient over theta over phi, and this would give us the meta gradient for the reward for the parameters in the reward functions, and this would be actually just the whole picture of how the optimization works in this case, so in this way we have a kind of show that we could combine the learning of Q function and the predictor and the learning of the predictor function into one step, and this is just one kind of framework of how this algorithms works. So the policy pi is it's a kind of updated through this like the critic from Q function, and it interacts with the environment, and also basically the data would be relabeled by this reward function that we trained through this kind of implicit gradient, and the human preference was used to update this to jointly update the reward function and the Q function here, and so basically this for this optimization algorithm, so actually the inner loop and outer loop can also converge to the stable point, which I would just skip the details here, and so before we go to the experiment, so if there are any questions, please also feel free to ask. Feel free to ask when I was talking, and let's see here. I got okay. So here are some. So here are the example tasks that we have used in the paper to evaluate its performance in terms of sample efficiency. So these are the Majorgo tasks of half cheetah and this kind of worker robot, and the other 6 tasks are like MetaWatt for to manipulate the robots to use the hammer to open the door or to press the button, etc. And so basically here are some experiment results. So experiment results in terms of the comparisons of sample efficiency. And as we noticed that actually here in terms across these tasks, the number of feedbacks that we have used is actually dramatically reduced. So now it's for example for the door open task, it's only using 1,000 feedbacks comparing to the previous works that requires 500,000. And so if we look at this curve, so the upper curve, that is the blue curve, that is soft act critic, that is actually the upper bound because it's not the preference-based algorithm. It is using the ground truth reward. So this is so the performs best for the obvious reason for the using ground truth reward. And so for our algorithms, meta reward net is in this purple curve. So basically, we see that it's kind of comparing to the baselines, it is converging faster and also converging to the better performance in terms of success rate in completing the task. And actually for this just the results for MetaWatt, and for the DeepMind control task, it's like show the similar results. And so next I want to show some kind of demos. So these are like several demos that's generated by our agents that are trained from the purely from the feedback without any reward signals. So it seems that they are kind of working well with this framework of training. And so any questions? Yes.
I'm just curious. So it's with human values. So you need to find where to source that information from. How do you go about automating that part to make sure that it is reflective of an actual person's preferences rather than an approximation learned just from a whole bunch of people sitting together and then you learn all the people that it is their preference? Online settings versus offline settings.
So I think the question is like for the human preference, would that be kind of stable or would that be kind of dynamic?
Yeah, in some way.
Yeah, actually this is a very good question. So basically, currently in this line of works, we assume that the human preference is stable, and it's kind of they have some kind of fixed preferences, and we just query them so that it give us their preference, and we do the update of like a learning of the agent. But I would think that the human's preference can be dynamic. It can change it can change with time, and also it can be kind of manipulated, which would be some kind of open questions that I think we'll also discuss a little bit in the challenges part. Okay, great, thanks. And so this is all for this. This is all for this for this part. And and also for the another challenge that we mentioned. So if we transfer this agent to some new tasks, do we need to realign this agent to the new task to the new task? And how could we kind of minimize the cost associated to that? So if we nail this down to a kind of if we nail this down to a kind of robot manipulation task, the question would be, for example, we have a source task of pushing a button, and we have a target task which is maybe like open the door. So could we, and we have the human's labels from the source task. So could we shift this information to the target task, or could we reuse this preference information from source task to inform how the agent need to perform in the target task? And so actually this is kind of in our recent work we have done a little bit of exploration for this. So firstly the answer is yes. So we could do that, and so I'll tell you how we do that and how that. Whether it works. So what we have done. This is kind of the techniques that we use is kind of distance alignment metric. So it's called optimal transport. So we have this kind of source task, and it has trajectories. Like it has a lot of data with like for example with the trajectory pairs like x and x prime, and we know it's x prime, and we know that its preference label is a +1 or -1, and then we have a target task where we have a lot of trajectories. We could sample this kind of pairs, like sample these pairs like y and y prime, but we don't know the labels for this pair, whether it's prefer y over y prime or on the reverse. So, and so what we have kind of tried so far is that so we could, based on this Gromov Wasserstein alignment metric, we could build a kind of transport matrix between the trajectories in source task and in source task dataset and a target task dataset. And then it's kind of this kind of transport matrix is kind of indicating the similarity or alignment between the trajectories from the source or target tasks. And based on this, identified the relationships between the trajectories from source task and to the target task. And when we do the sampling of any two kind of trajectory pairs from the target task, we could compute the labels of whether this whether the trajectory y is preferred over y prime based on the labels that that we have from the source task. So this is kind of an example. So we assume that we have 4 trajectories, and we could solve this kind of transport matrix that shows that aligns these trajectories from the target task to the source task, and then we could transfer this preference information. So for example, in the target task, we get these 4 trajectories. We want to have the pairwise preference label to be recovered. So it's like, for example, for this case, it'd be like y1 is preferred over y2, 3, 4, and y2 is kind of better over 3, 4, like that. And this is just kind of general idea of how this kind of preference information transfer would works in this kind of setting. So in this kind of setting, so when you are facing with a new task, you might not need to start from scratch to ask humans of okay, what do you like, what you don't like. So you could try to leverage the data of existing tasks that you have, and so this is just kind of the indication of the GW alignment metrics that we have used. It's kind of a little bit complicated distance metric, which is you can also check the details in the papers, and I'll go explain that a lot. And so basically here is here are some kind of here are some examples of videos. So the first line would be the videos from the source task, which is the push the button, and the second line would be the videos from the target task. So we want to build. So we have the preference labels in the source task, and I want to build up the labels for the target task. And this is actually what we obtained for this task in this scenario. And so basically it's just allow us to compute the labels for the target task, and then based on the computer labels for target task, we could do the standard framework for the RLHF, which is train the reward function, and based on reward function, we could do the second steps of training the reinforcement learning agent based on the reward signals that we have. So basically, this is just in general a kind of a technique that would allow us to relabel the trajectories in the new tasks that we might not have the information of any human preference labels. And so this would be actually the 2 example works I'd like to introduce of how reinforcement learning from feedback works, and how could we how that works, and how could we improve its efficiency in terms of using less human feedback. And how could we and at a further step, how could we just do the zero-shot alignment in the new task, like just leveraging the preference information from existing tasks. And so this just kind of summary of this content. And so next, I would like to discuss some kind of questions, open questions, which I might also not have an answer to that. So when I started working on this reinforcement learning from human feedback, and in the first instance, I was treating that to be using humans' preference to improve the single agent capabilities of doing some certain tasks. But gradually, when we look at this problem, it's a kind of this problem is kind of a human and AI interaction problem, human AI coordination. So we want this AI agent to be able to learn the human's values. And currently, the existing kind of works are mostly discussing this single directional alignment. So humans see that okay, they want they want A over B, and the AI agent just need to inference this kind of preference or values, but preference values, but actually we might also be, this might also not be always the case. For example, AI, the humans might also look at the AI agents' behaviors and see that, okay, maybe at which time step I might need to intervene to see that, okay, I need to give a preference in some cases, so that I don't need to be the humans can be a bit active in terms of when to intervene to tell the AI agent that, okay, I need to tell you that at this time you would consider to do something, to something, or to consider my value, and actually, in terms of the human feedback, so currently, as also one student asked the question, so currently many of the works assume that the human's feedback is stable, but actually, and is stable and also consistent. But actually, there might be also lots of different. Also a lot of various issues that might exist. So, for example, there might be inconsistency in even for single person's feedback, there might be the inconsistencies. So if you ask this person whether you prefer, like you prefer, for example, the apple over prefer apple over banana, and prefer banana over the pear, and prefer pear maybe over apple again. So this kind of inconsistent in one's preference. This is something that kind of that is kind of missing from literature yet. And another thing that there might be like for example kind of a group of people providing the preference to the agent at the same time, and so there might be kind of for this kind of group of people there might be some conflicts among these people's preference. So how would we coordinate? How would we coordinate the kind of conflicts among humans in terms of the provided preferences to ensure that everyone's preference may be fairly represented or not? And another important another question that is actually quite important or quite urgent at the moment is kind of the on the adversary side. So basically we have assume that we also have multiple humans and they express their preference, and so it's kind of a voting game. So they vote one agent to represent the group of people's preference, but basically whether this voting could be manipulated. So, for example, maybe some of the adversaries might misrepresent their preferences, so that this AI agent's behavior might be misled to some different directions, and on the other hand, during the interactions between the AI agent and the humans. So would the human's preference stay stable, or would the human's preference being manipulated or being shifted by the AI agent? So this question actually it's being asked or discussed in recommender systems, which is actually proved to be true, that the user's preference can be manipulated through the interactions with recommender systems. But currently, as people are relying more and more on the language models, we are spending a lot of time to ask questions on language models, whether our opinion or whether our preference or whether our opinions on some matters can be manipulated by this kind of chatbot. So this is one question that is question that has received almost zero attention yet. But actually I would think that it's a pretty urgent question at the moment. And so that's all about this. And at the last, it might be some information of our research group. as our research group, as we mentioned, we work on mainly on two threads. One is enable the agent to perform the robust decisions, and the other is to promote the collaborations of among the multiple agents. And we have worked on some traditional topics of scalability, credit assignment, communications, and recent topics which are the human AI coordination and agent alignment from the human's preference. And so that's I think that's all for what I want to say for today. Thank you.
Hello, sorry, I dropped my microphone. Cool, thank you very much, Yali. Again, same thing with Slido, got some questions in there already, feel free to add some more. First one at the top for you right now is, are you aware of any research evaluating the effect of RLHF and similar techniques on cooperative AI metrics, such as cooperation in general-sum games?
Mm-hmm. So the evaluation of RLHF, and so actually, I think that actually for the IIHF, I think currently the current evaluation is mostly about the human experiments. As I mentioned, for example, in the early picture that my early slides that I showed in the InstructGPT. So basically, they used the human to evaluate whether what response they prefer. Generate the responses generated by the IHF feedback, and the responses generated by some supervised fine tuning, and what's preferred. They use the kind of human to evaluate whether it's a kind of to do the evaluation, and actually another part for the question is about the cooperation in general sum games. So I think this is one very interesting question. But currently, I would say that there is, I guess, there might not be lots of answers to that yet. So the cooperation of so the agents, the capacity, capacity of agent capacity of cooperation in general sum game or in self-interested game. So I think there. So actually, we have done some kind of recent attempts to evaluate that not in general sum game, but in the kind of two-player cooperative games. So evaluate the agent's capacity of collaboration with other agents. So it's we consider this kind of population-based training and build this kind of pairwise collaboration pair and evaluate which agent is preferred by other agents in terms of achieving higher rewards in collaboration. So but for the more general case, I think it's definitely was some question that need efforts.
Okay, thanks. Next question on the top of the list is, humans have biases that impede cooperation, such as zero-sum bias, the tendency to think of oneself as playing a zero-sum game. Should we try to prevent such biases by shaping AI via RLHF, and if so, how?
So for the human bias, for this, and for many of the existing works, I say that they don't. So many of this work, as in the works that I discussed, so we don't consider this kind of bias. So we consider that the human's values is the first and foremost important. We just try our best to align this AI agent to be consistent with human's values. But actually for this kind of bias, or maybe for example, sometimes some kind of malicious preference, I think we might. So I guess I don't have an answer for this yet, but I guess it's kind of related to the question that we discussed before. So whether agents needs to have a preference. So agents also need to develop this kind of preference. For example, humans may say that human may say that let's cooperate to for example to kill somebody, but agents would just react that that's not a kind of proper preference. We wouldn't just be kind of kind on good to the society.
Okay. Next question is, so RLHF made ChatGPT possible which raised investment in AI and accelerated the development of AGI, artificial general intelligence. How can we work on safety without accelerating the AI race?
How safety without accelerating the AI
Yeah.
race.
So I guess the idea is that because RLHF ostensibly at least seems like a kind of good thing, it's kind of helpful for pushing the models where you want to take them, but it's also potentially, I suppose, one of the main or more important reasons why models like ChatGPT are actually so useful, which in turn has then kind of given lots of investment into these technologies and has kind of created what appears to be, at least at the moment, a little bit of a race. Hopefully it will not stay that way. But
yeah. So actually, I think that so basically, in terms of the safety, it's a everlasting topic, and we need to consider it all the time. So consider all the time. So how could we? So even for the current development of AI, we do think how to regulate it. How could we regulate its development? How could we make sure that it is safe? It is not generating some kind of for example, unsafe or hateful comments. So basically, I would say that actually safety is kind of one of the values that we need to consider in developing this kind of AI agent. And also, as I mentioned, as I mentioned in one of the open questions, so to make sure that a human's preference is not exploited or is not manipulated maliciously by this kind of chatbot is also one of the safety issues that I would consider relevant in terms of the progress of IIHF.
Okay, cool. I think we're going to pause slightly early because the next talk is happening remotely, and so there'll be a little bit of setup that needs to happen in the meantime. So before then, we'll just give Yali one more round of applause, please.
Okay,